In this video, we're going to look at another application of work integrals. A cylindrical tank with a radius of 1 meter and length of 2 meters is full of crude oil and is buried 3 meters below the ground. That means the bottom of the tank is 3 meters below the ground. How much work is required to pump all the oil through an outlet pipe 1 meters above the ground? Gravity is 9.8 meter per second squared. The density of oil is 900 kilograms per meter cubed. We're going to exploit the circular symmetry of the tank so that we can make our computations easier. Namely, the integration. We want to make the integration easier to do. We're going to choose y equals 0, which is the x-axis, at the center of the circular end along the axis of symmetry of the cylinder. And the cylindrical tank is lying horizontally under the ground. Alright, so let's start with a diagram and defining some variables. The most important part of this diagram is basically the cross-sectional slice and the distance that this slice has to travel so that the slice of oil can be pumped out of the outflow pipe. So here's the cross-sectional slice here, and we're on a coordinate system. So this is the y-axis here, then the x-axis is like that, goes through the origin. So this is x, x represents half of the width, and this is 2 meters here. So the entire cross-sectional area is basically 2x times 2. So y equals -1, this is the bottom of the tank. Y equals 0 is the center of the tank. Y equals 1 is the top level of the tank. Y equals 2 is the ground level. And y equals 3 is the outflow pipe, which is 1 meters above ground level and 2 meters above the top of the tank. The key concept here is that a cylindrical tank lies between y equals -1 and y equals 1. And every rectangular cross-section at height y has to be raised 3 minus y meters to be pumped out of the outflow pipe, which is 3 meters above the center of the tank. Alright, so here we have a side view of the tank. We have y equals -1, which is the bottom of the tank. We have y equals 1, which is the top level of the tank. And we also have this distance, which is y. This is the distance from the rectangular slice to the x-axis. We have y equals 2, which is the ground level, and y equals 3, which is the outflow pipe. So the key concept here is that a cylindrical tank whose bottom is buried 3 meters below the ground lies between y equals -1 meters and y equals 1 meters. So it lies between y equals -1 and y equals 1. And every horizontal cross-section of oil is a rectangle with width of 2x meters. Width is equal to 2x. And length of 2 meters. This is very important to conceptualize. So let's do that. So 2x, this part here, this is the width of the rectangle. Let's also draw the length. The length comes out like that. So because this is the cross-sectional slice, which is a rectangle, and this is 2 meters. So 2x times 2 gives you the cross-sectional slice. So the cross-sectional slice, A of y, is equal to the width of the rectangle, you're looking at it from the top, 2x, times the length of this cross-sectional slice, the length of this rectangle. And the area of a rectangle is simply width times length. 2 times 2, we get 4x. Of course, we have to get this cross-sectional slice as a function of y. All right, so since all the horizontal cross-sections perpendicular to the y-axis are rectangles with width of 2x meters, so the width is equal to 2x, the length is equal to 2 meters, then the cross-sectional slice as a function of y is simply 2x width times length. That gives us 4x meters. Now we're going to apply Pythagoras to express x in terms of y so we can get the cross-section slice as a function of y. Let's look at a diagram. So here's the Pythagoras that we're going to apply to this triangle. Here's x, which is half of the width. This is y, the height of this slice from the x-axis. So we can apply Pythagoras and get x squared plus y squared equals 1 squared. So let's do that. So we have x squared plus y squared is equal to 1 squared. Isolating for x squared, we get x squared is equal to 1 minus y squared. Solving for x, we get x is equal to plus or minus. We'll only take the positive. X is because width has to be positive, and x represents half of the width. Root of 1 minus y squared. So cross-sectional area, A of y, is 2x times 2 is equal to 4x. And solving for x in terms of y, we get 4 root of 1 minus y squared. Now let's define the cross-sectional volume as well. So differential volume, the volume of one of these rectangular slices of oil. That's going to be A of y times dy. And we defined A of y to be 4 root of 1 minus y squared times dy. This is the volume of a rectangular slice. Let's find the differential mass, dm. dm is going to be rho times dv. Well, the density is 900. The density of oil in this case is 900 kilograms per meter cubed. So we have cross-sectional slice as 4 root 1 minus y squared times the density of oil, which we take to be 900 kilograms per meter cubed, times dy, times the height of the slice. The differential force is gravity times differential mass. So we get 4 root 1 minus y squared times 900 times 9.8. So let's break that down. Here's the cross-sectional slice A of y. Here's the density of oil, rho oil. And here's gravity times dy. So what does this represent? This is the force needed to overcome gravity acting on the mass of oil in this rectangular slice at height y. All right, so let's define differential W, the work required to pump this slice, this rectangular slice, over the outflow pipe. Differential W is going to be distance 3 minus y times differential force, dF. So we get 4 root 1 minus y squared times 900 times 9.8 times the distance that this slice has to travel to be pumped out over the top. Let's break this down. This part, this is cross-sectional slice, the area of this rectangular slice. This is going to be the density of oil. This is gravity, and this is the distance that the slice has to travel to the top. Very important to have the right setup. So dW represents the work required to pump out this rectangular slice of oil 3 minus y meters through the outflow pipe. Now the key concept is this 3 minus y. Let's define this and let's prove that this is actually the right quantity. This quantity represents the distance that each rectangular slice of oil at height y must travel to be pumped out of the outflow pipe. So let's check that for the bottom slice and the top slice, because if this quantity, if this distance works for the bottom slice and the top slice, it has to work for all the slices in between. So let's check y equals -1. Y equals -1, this is the bottom of the tank. We get 3 minus y, that's the distance that this slice has to travel to the top. 3 minus -1 is equal to 4 meters. Does this make sense? Let's go back to the diagram. The bottom slice, clearly the bottom slice has to travel 1 plus 1, that's 2, plus another 2, that's 4. Clearly it has to travel 4 meters to get to the outflow pipe. Now let's look at y is equal to 1, the top of the tank. Plug it into 3 minus y, and we get 3 minus 1 is equal to 2. Does this make sense? Let's go back to the diagram. The top of the tank is 1 meter below the ground, and the ground is 1 meter below the outflow pipe. 1 plus 1 is 2, so the distance from the top level of oil to the outflow pipe is simply 3 minus 1 is 2 meters. That also checks out. And if it works, if 3 minus y, if this distance works for the bottom slice and the top slice, it has to work for all slices in between. All right, so step 2 is to set up a definite integral and find the work required to pump the oil out of the tank. So differential W is equal to 4 root 1 minus y squared times 900 times 9.8 times 3 minus y dy. So let's break this down. This is cross-sectional slice, the cross-sectional area of a rectangular slice. 900 is the density of oil. 9.8 is gravity. 3 minus y is the distance that every rectangular slice has to travel to be pumped over the top. All right, so the work is going to be the integral from -1 to 1, 4 root 1 minus y squared times 900 times 9.8 times 3 minus y dy. Now all these constants can be pushed out of the integral, they can pass right through, so we get work is equal to 4 times 900 times 9.8 integral from -1 to 1 root of 1 minus y squared times 3 minus y dy. Let's split up the integrals and evaluate each integral separately. So the work is going to be equal to 4 times 900 times 9.8. Now multiply 3 times root of 1 minus y squared, so times 3, integral from -1 to 1 root of 1 minus y squared dy minus 4 times 900 times 9.8 integral from -1 to 1, and we get y times root of 1 minus y squared, so we get y root of 1 minus y squared dy. We're going to evaluate these integrals separately, then add up the two results and get the work required to empty out the oil. All right, so here we have work is equal to, we just simplified these numbers, did some number crunching, put them into calculator. So integral from -1 to 1, root of 1 minus y squared dy, and we have integral from -1 to 1, y times root of 1 minus y squared dy. We split up the integrals, and we have to evaluate it separately. Let's look at the first integral. Integral from -1 to 1, root of 1 minus y squared dy. The easiest way to solve this integral is to realize that the integrand happens to be a semicircle of radius 1. And the integral represents the area under the curve. So that's simply going to be pi times radius squared, radius is 1, 1 squared divided by 2 is equal to pi over 2. All right, now let's look at the second integral. Here we have integral from -1 to 1, y root of 1 minus y squared dy. Now, there's two ways to solve for this integral. One way is really quick. If you happen to recognize that the integrand is an odd function on a symmetric interval from -1 to 1, then what happens is the areas cancel out. So basically it goes like that, and the total result will be 0. But we're also going to show the substitution method because that may not come to you in the heat of an exam. So we're also going to apply the substitution method to show this. We're going to let u be equal to 1 minus y squared. Differentiate both sides, we get du is equal to minus 2y dy. And if you solve for y dy, you will get du divided by minus 2. So applying u substitution, integral from -1 to 1, y root of 1 minus y squared dy will be equal to -1/3 times 1 minus y squared to the power of 3/2, evaluated from -1 to 1. Let me put this in a box to organize things. All right, so now we can apply fundamental theorem of calculus, and we're going to get -1/3 times, plug in the upper limit in, put 1 in, we get 1 minus 1 squared, that's just going to be 0, 0 to the 3/2, minus 1/3, and put -1 in, we get 1 minus 1 squared, that's also going to be 0 to the 3/2, so the result is 0. And so either you can use odd symmetry or you can use U substitution. Both results will agree, of course. The answer is 0. All right, so what we have is we split into two separate integrals. The first integral is pi over 2. The second integral is 0. So let's simplify this. The work is going to be 105840 times pi over 2 minus 35280 times 0. So the work will be 52920 times pi minus 0, and this comes out to 52920 pi joules of work. So therefore, it takes 52920, essentially 52,920 pi joules of work to pump all the crude oil out of this cylindrical tank. If we decimalize this, the work comes out to be approximately 166,253.08 joules. Let me spell that correctly. J-O-U, there we go. All right, thanks.